Okay, one more example here from the first part of chapter 13. Separate note document for the second part. I kind of have it broken up into topics, rate law versus integrated rate laws. So looking at the same type of problem here, we've got a reaction, we've got a set of data about different runs of that reaction and how their rate is affected, and we want to figure out the rate law. So again, the basic form for rate law is that the rate is going to be equal to the rate constant times the reactants. So we've got NO here and H2, just two reactants this time, so that's all that will show up in the rate law. But each of these will have some exponent associated with it. That's part of what we need to figure out here to get a handle on the rate law. So again, we want to look at the data in the table, kind of compare how changes in the concentration of the reactants affects the rate. So let's start by trying to figure out the effect of changing the concentration of NO here. So I look up at the table, and I can see from experiment 1 to experiment 2, 6.4 to 12.8, same exponent. That's a doubling of the concentration. So from 1 to 2, I double the concentration of NO. In that same set of experiments, H2 or hydrogen here stays the same. So that's good. That's what I'm looking for, is where I can eliminate any effect from one of the components or all but one of the components. If I can eliminate any effect of changing the concentration of hydrogen, I can focus in on how changing the concentration of NO affects my rate. Now, if I look over here at rate, I go from 2.6 to 1, but what I need to be careful of here is the exponents changed. So this is 2.6 times 10 to the minus fifth. It's going to 1 times 10 to the minus fourth. Now, if you're unsure, go ahead, use your calculator, and divide these out. So 1 times 10 to the minus fourth divided by 2.6 times 10 to the minus fifth. That's 3.846. That is pretty darn close to 4, right? And in fact, what we're looking for here, all of the possible ways the rate can change is a function of how the concentration changed. Now, I'll talk about that in just a second. But that's 4 times faster, right? Within experimental error there. So thinking about the rate law again here, what we're doing is comparing the rate of experiment 2 to the rate of experiment 1, and we want to compare that to how does the concentration of NO in experiment 2 relate to the concentration of NO in experiment 1, and that whole factor is going to be raised to whatever exponent we decided, and I put X up there. So in this case, the ratio of the rates is 4. The ratio of my concentrations is 2, from 2 to 1, and that's to the X power. Well, that means X is equal to 2. Now, we would describe that as second order. The reaction is second order in NO because the exponent is 2. Now, realistically, this value that we get for the exponent has to be an integer. It has to be 0, 1, or 2. It really can't be a higher integer. That would just be too complicated in terms of pieces of molecules connecting together, in terms of how a reaction happens. There are some weird cases where it can be fractional, where it's like 1/2. I try to avoid those because I think they're just a little too complicated at this point in learning about what kinetics means. Okay? But we're looking for a value of 0, 1, or 2. So if we know the rate doubled, there are really only 3 possibilities here. 2 to the 0th power, 2 to the 1st power, or 2 to the 2nd power. So if we double the concentration of one reactant, what should happen to the rate is it should either stay the same, which would mean the ratio of rates is 1. It should double, which would mean the ratio of rates would be 2, or sorry, be to the 1st power. Or if the order of the reaction is 2, the ratio of the rates should quadruple. Okay, so if it comes out in between, like 3.84 in this case, that's a lot closer to 4 than it is to 2. So sometimes with experimental error, they won't be exact like they were in the first example. Okay, so second order in NO, we want to do the same thing for hydrogen here. in this particular reaction. So for hydrogen, if I look from 1 to 3, NO stays the same. Right? So that means I can just focus in on what happens to the concentration of hydrogen. From experiment 1 to experiment 3, that's 2.2 to 4.5. That's basically doubled, maybe a little error in terms of making the solutions. 2.6 to 5.1, both 10 to the minus 5. So my hydrogen doubles, my rate doubles. Right? So if I compare the rate of experiment 3 to the rate of experiment 1, that is 2, because the rate doubled. The concentration of hydrogen in experiment 3 relative to the concentration of hydrogen in experiment 1, that's raised to the y power here. That's also 2. We doubled the concentration of hydrogen. So that means y is equal to 1. And those are the only two reactants, so there's our rate law. The rate of this reaction is going to be equal to the rate constant. Concentration of NO is going to be squared, or to the second power, and the concentration of hydrogen is going to be to the first power. Okay, so we successfully identified the rate law. Now, what's very common for this type of problem is a second part to the problem, and that would be to determine the value of K. So let's add that in here. Part B, if you will, of the problem would be calculate K. Now, we could calculate K because we have data up here for every component of this reaction except K. So I can rearrange this equation just by dividing both sides by NO squared and the concentration of H2. So if I take the rate and I divide by the concentration of NO, but squared, and by the concentration of hydrogen, that will give me the rate constant for this reaction. So just take experiment 3 and plug that data in. 5.1 times 10 to the minus 5th. Now, that's a rate, so that would be molarity per second. Concentrations here on the bottom would be in molarity units. So 6.4 times 10 to the minus 3rd, that's molar, and that's going to be squared. And 4.5 times 10 to the minus 3rd, that's also molar. Now if I multiply all this out, 5.1 times 10 to the minus 5th divided by 6.4 times 10 to the minus 3rd divided by 6.4 times 10 to the minus 3rd divided by 4.5 times 10 to the minus 3rd. And don't forget that this is squared, so I divided by it twice here. There's other ways you could punch it into your calculator that are maybe a little more efficient. Round that, be 277. Now, actually, it's all two significant figures, so we round that even further to 280. But one of the things you really want to be careful of here is the units on the rate constant, and we will see in the second part of the chapter how important that is. But the units on the rate constant will change depending on the order of the reaction. This is a third order overall reaction. Remember we said it's second order in NO, it's first order in hydrogen. You add those together, this is third order overall. This molarity here would cancel with 1 on the bottom, but only 1. So we'd still have the seconds here on the bottom of the fraction, but we'd have 2 molarities on the bottom of the fraction. So the units here would be 1 over molarity squared times seconds for K. Now that's often written as m to the minus 2, s to the minus 1. But you can also split up molarity. Molarity on the bottom is liters per mole. So this could be liters squared per mole squared second. All of those should, actually no equals there, all of those would indicate a third order overall reaction, and that's going to be an important piece of information to pick up on when we get into integrated rate laws in the next video.